Okay, thank you, Alex. So yeah, I'm Edd Barrett, and I'm going to speak for a little while about the Rust programming language, and my screensaver is going to come on. Okay, so first a little bit about me, and then we'll get on to the main part of the talk. So I'm a research associate at King's College London. I actually live here in Canterbury but commute. Before that I was a postgrad just over the way there in Cornwallis. So we're actually maybe 100 metres away from where I used to work in the office there. And in my spare time, I'm an OpenBSD developer, so I port various bits of third-party software to OpenBSD. And that's where you can find me on social media. Right, so I promised you a talk about Rust. Do we have any Rust devs in the audience, by the way? Anyone used Rust? One person has used Rust. Okay, fine. So this is not going to be a talk where I teach you the programming language. So maybe that's what you're expecting. No, what I'm going to actually do is I'm going to motivate why a language like Rust actually exists. And to do so, we have to start by talking actually about what came before, which is C and C++. Now, if I ask the same question, has anyone used C or C++, I imagine a lot of hands will go up. Anyone? Right, so these are fairly popular languages, as we shall see. So this is going to serve as a starting point for my talk, so let's go. So, in case you've not heard of C and C++, these are both what we call systems programming languages. So what do we mean by a systems programming language? Well, typically we're talking about a programming language which operates either very close to the metal, so close to your chip, or very close to the operating system itself. And there are a spectrum of applications which are very well suited to that kind of programming. So utilities, operating system utilities, for example, are often written in C and C++, etc. So these are also very old languages. So C in 1972 and C++ in 85, so several decades old. So given that these languages are so old, they are still surprisingly popular languages. So this is a snapshot of last month's TOB index. So the TOB index is a company who does a survey of the popularity of various programming languages. They use a magical algorithm which I'm not sure anyone really knows how it works, but what comes out is a listing of the most popular programming languages. So we can see here that the most popular language in November 2019, was Java, and then C. And then underneath that is Python, and then C++. So we see that two systems programming languages are actually within the top 5 according to the TOB index. So they are very popular languages is what I'm trying to get across here. And it's not the case that they were just popular in November 2019 either. This is showing the popularity of the languages across time. So the x-axis is time, and the y-axis is the rating. Apparently it's a percentage. The unit doesn't really matter. What is important here is that, so C is the black line here. So we can see that C has always been a popular language, and it's only in recent years that Java has become more popular than C, and I'm willing to bet that that's the rise of Android. I'm not sure. And then C++ is this, it's the green line, which is actually on a bit of a decline. So C++ is kind of on the way out, but it's still the third most popular language. So, why am I telling you that these languages are popular? Well, popular languages have lots of people using them, and there's lots of code coming out from languages like C and C++. I imagine that if you did, GitHub surveys, then these languages would also be very high in the rankings. But given that these languages are so popular, there is actually a fairly large problem with these languages. Does anyone want to hazard a guess as to what I'm going to say? It's one word. Mex knows it.
Yeah, I've seen the slides.
Oh, have you? Okay, fair enough. So these are unsafe languages. So what do we mean by unsafe? So typically when we talk about safety, we're talking about one of two things. We're talking about either memory safety or thread safety. There may be other kinds of safety, in fact, but these are the two main ones. And arguably, thread safety is a kind of memory safety. So thread safety is a bit too complicated to go into in only a half-an-hour talk, so I'm actually going to focus on memory safety. And this is going to really motivate why I think Rust is a good thing, and why I basically think that it's wonderful that someone is actually trying to move on from C and C++. So let's talk about memory safety. What is memory safety? In a language like, say, Python or JavaScript or Java or any of these kinds of languages that have a virtual machine, typically you don't really care about what you're doing. You don't care about how you ask for memory. Memory just pops out somewhere, and then when you're done with it, you just forget about it, right? It just disappears. And the way that that happens is there's a piece of the runtime called a garbage collector. And what the garbage collector does is it sits there in the background and tries to figure out when you're done with things, and it throws them away when you're done. So you never have to think about, when you should ask for memory and when you should then give memory back to the operating system. In a language like C, it's all explicit. So this is a very synthetic example, but it should serve the purpose. So what we've got here is you've got a program which allocates a string using this malloc function. That means I would like 16 bytes of heap memory, please. That's basically what that says. And then we copy into it the string hello. So now we've got this string hello in memory, great. What do we do with it? Well, we print it. We then pass it to a function called doStuff, and then we print it again. So what does doStuff do? Well, actually, the implementation of doStuff doesn't really matter. What is important is that there is an error condition here, and the programmer has decided to say, I'm done with that memory if an error occurs. However, this is incorrect. This is incorrect because when we come back from doStuff, we actually print the string a second time, if you recall. So, if an error occurs, and we free the memory, and we then print the string, then we've actually printed some memory which is now freed. This is called a use after free problem. And the C compiler will quite happily let you do this. It's an incorrect C program, you shouldn't do it. So what we're going to refer to these things as memory errors from here on out, right? So you've just seen a use after free error. There are various other kinds of memory error. There are double frees, there are a whole class of things called buffer overflows, there's the wonderfully named dangling pointer, and then there's just freeing something which you never actually asked for in the first place, and that is also incorrect. And what I really want to get across here is that really experienced programmers who are proficient in C and C++ make these kinds of mistakes all of the time because the language makes it very, very easy to make these mistakes. So, what happens when you do this, when you make one of these memory errors? Well, actually, what a computer scientist would say is, we invoke undefined behavior. So it sounds very formal, right? That's just a fancy way of saying absolutely anything can happen, right? So, if you're lucky, your program carries on, and you don't notice. Rarely. Okay, the other thing that typically happens is your program crashes. That's irritating because your program's crashed and you can't carry on doing what you were doing. You know, if that was Microsoft Word and you've got your thesis in it, for example, and it's crashed, that's pretty irritating. I think you'd agree. However, the third thing that could happen is the program may continue, but it may behave in a way that it wasn't designed to do. And that has implications which are very, very irritating, as we shall see. So as it happens, when I ran the program that I showed you before, and the error occurred, and we freed the memory, and then we printed the freed memory, the first print is correct. The second print prints a whole bunch of unprintable characters. So there we got the third case. The program continued, but it didn't do the right thing. As you can imagine, that's really bad as well. Imagine that was your online bank, and you just deposited £200 and it took off £10,000, for example. Clearly you don't want that in your programs. Right. So, not only is it irritating when your program crashes and when it doesn't do what it's supposed to do, these memory errors also are security vulnerabilities. So what do I mean by a security vulnerability? I mean that there are people on the internet with less than desirable traits who don't look like that, actually. And what they're very good at, actually, is they're very good at knowing how memory is laid out in your program, and if they know that a program contains one of these vulnerabilities, they often can kind of persuade the program to do something that they wanted to do, not what you want to do usually. So typically, what they're trying to do is they're trying to steal your sensitive data by using one of these vulnerabilities, or they might want to run what I've called naughty programs on your system. So they might want to mine Bitcoin, they might want to install a botnet, you name it. There's, you just don't want random people on the internet with access to your machine, is basically the point. And these memory errors give them the foot in the door to try and exploit your system. And this is what I'm going to talk about for the most of this talk now. So how bad is this problem? And if this only happened, say, once in the history of computing, then we wouldn't really care, would we? but it's actually it's more frequent than this, and I'm going to try and demonstrate the extent of the problem in the next few slides. So it's a common enough problem that we have an online database called the CVE database. So this is the Common Vulnerability and Exposures database. And this is a database of basically these kinds of errors and more, but a large chunk of them are memory errors. So when someone finds a bug in, say, Microsoft Word, and they find out that it's a memory error, what they can do is they can submit it to this database, and then it's put in public view for people to then patch their systems and be aware of this problem, for example. This is one from November this year. It happens to be Adobe Reader, so the very popular PDF viewer. What this one basically says is there is a use after free vulnerability, and if it's successfully exploited, it could lead to what they call arbitrary code execution. What this means is basically a third party can run whatever they want on your system, and that's how you get your botnet or your Bitcoin miner on your system. So this is not the kind of thing that you want to hear about in Adobe Reader, which is a very popular piece of software, I should add. There were about 10 for Adobe Reader, by the way, when I was doing the research for this talk in November. So maybe that's an indication of the quality of Adobe Reader. I'll leave that up to you. Right, so at the time that I was doing the research for this talk as well, I put out a tweet saying, does anyone have any interesting statistics on memory safety errors? And 2 people got back to me. The first was Cristina Cifuentes. She is a security researcher. She's quite famous in the field, actually, but she said, have a look at this paper. It's got a couple of things that I'm sure you'll be able to use. And indeed, she was right. So she analysed the CVE database and found that from 2013 to 2017, there were just under 6,000 buffer errors reported in the database. And that turned out to be about 20% of the data. So the implications of that are basically 20% of the reported data could lead to someone breaking into your system if the scenario is correct. I should also mention that not all of these errors are reported. Of course, people just have to have the motivation to report them, but also they're kind of worth money, so people tend to sell these on the dark web. If you've got a really juicy one, you can sell it for good money, and it won't end up on the CVE database until someone finds it. And I also found it interesting that the cost of a data breach on average was $3.86 million US. So data breach is where your data gets stolen. This is one of the things that can happen if you are exploited in this way. The second person that got back to me was Alex Gaynor. Now he is actually on the development team of the Rust programming language, and he's got a blog. And in this particular blog post, he had some really quite, should we say, damning statistics. So a recent study found that 60 to 70% of vulnerabilities in iOS and macOS are caused by memory unsafety. Microsoft similarly estimates that 70% of the vulnerabilities in their products over the last decade have been caused by memory unsafety. And Google, again, 90% of Android vulnerabilities they reckon are due to memory unsafety. So when you get your patch on your Android phone, your security patch, it's fixing things like this. I must admit, I didn't realize it was this bad. So how bad is it? It's pretty damn bad. It's pretty bad. So what can we do about this? Well, there are a few things we can do. The first thing we can try and do is to try and detect and fix these bugs using either dynamic analysis or static analysis. So I guess you guys know what dynamic and static analysis is in a room full of coders, right? So this is things like, when we're talking about C and C++, it'd be things like Valgrind and the Clang static analyzer and things like that. The problem with this solution is they don't find all the bugs, and also you have to remember to run these things, because if you ship code to the users and then run these things and find the bugs, it's too late. So I'd say that that's an imperfect solution. Then there are operating system level mitigations. So this doesn't really solve the problem either. This basically limits the damage in the case that one of these things happens. So it tries to make it really hard for attackers to do what they want to do once they've got a foot in your system. So again, not a perfect solution. And you could, of course, use a managed language. So you could use, say, Python, Java, JavaScript, any one of those languages, because there you don't have to deal with allocating and freeing memory manually. But the thing is that, as I said, the runtimes of those systems have that garbage collector, and depending upon what you're doing, a garbage collector may not be it may not be feasible for your targets. Okay, so there is a company called Mozilla, I'm sure everyone knows. What Mozilla are trying to do is something entirely different. So you know Mozilla because they build Firefox, right? And they are developing a language as we speak called Rust. So a bit of a marketing spiel lifted straight off the Rust website here. Rust's rich type system and ownership model guarantees memory safety and thread safety, enables you to eliminate many classes of bugs at compile time. So to unpack that, what this means is that first of all, you're going to find bugs when you compile the program, not when you run it. That's good because you can't ship it to the user if it didn't compile, right? So you'll catch the bugs before you ship it. Also, they're claiming here that the memory safety problems, like the one I showed you, are eliminated by the language as well. Thread safety as well, we mentioned that as well, but as I said, we don't really have time to go into that one. And they also want this language to be performant and productive. Right, so to demonstrate very briefly the kind of things that Rust does, here is the same use after free that I've converted to Rust. So it's the same program, just in a different language syntax effectively. So we've got our string here, we print it, we pass it to the do stuff function, we print it again. And again here, we have this drop, we have this drop, which is the same as free in C. It isn't strictly necessary to have this drop here in Rust actually. Rust will decide when to free things for you based on scope. But I put it here just for the sake of the example. So if you try and compile this using the Rust compiler, you get this error message. It's quite a big error message. It's quite hard to understand if you're new to the language. This was very hard to understand when I was new to the language. So the important part is actually this part here, value borrowed here after move. I'm going to go back one slide and explain what the Rust compiler is trying to tell us. Right, so what's happened is we've got a string s. In a language like Rust, there is the notion of ownership. So the variable s owns the string hello. When we then call do stuff, passing s, we actually give away ownership. It's like I'm holding the string and I pass it to do stuff. That's yours now. And I now have nothing. Right? So when we come back to try and print s, what the Rust compiler is saying is, you're trying to use something you've given away. You can't do that. And that may seem very strange. It seemed very strange to me the first time I used Rust. It seemed like an unnecessary constraint. But when you think about it, what it's actually done is it's made it impossible to construct a program where you can have a use after free error. Right? So that was called ownership. That's the concept there. Basically, things move around. You pass them around to people. There is another thing called borrowing and lifetimes. We don't have time to go into that one in great depth, but this is all about if you don't actually want to give something away, you can lend it to someone via a reference, and then there are various rules about what you can and can't do with references. So the C and C++ uses know a bit about references, I'm sure. So you have references, just there are some more rules on top of them, and they are constructed in such a way as to guarantee memory safety. So, starting to wrap up, basically through ownership and borrowing and lifetimes, what Rust is effectively giving us is compile time memory safety in a systems programming language and without a garbage collector. And that is kind of a new niche that we haven't really seen many mainstream languages that touch that niche. Normally you get a memory safe language with a garbage collector, or you get a systems programming language where you have to allocate and free memory manually. So I think this is a really good thing, because it means that those security problems I was telling you about can mostly become a thing of the past. Not all of them, of course, but a lot of them, anything based on memory safety, we don't have to worry about those, and we're just generally safer as citizens of the internet. And there are some companies who also think that this is a good thing to do. Of course, Mozilla think their own language is great. A lot of Firefox is now implemented in Rust, so they converted a lot of it from C++ to Rust. Microsoft have been very vocal about their adoption of Rust for various projects, although I don't recall what they were off the top of my head. Various parts of Dropbox are now written in Rust, and Yelp have a testing framework written in Rust. Right, so I've told you what I think is the most important thing about Rust, well, at least for me, because I'm quite security minded. But what else is good about it? Well, it has a good standard library. I don't know if anyone's tried to do generic data types in C, for example. It's really, really hideously annoying to do. Rust makes this easy, much in the same way C++ does, actually. So it has good multi-threading support, C doesn't. It's pretty portable. So most of the main architectures are supported. You can run it on your laptops and servers and things. You can now run it on Raspberry Pis, and they also target Arduino now as well. And it has a very active ecosystem, which is always good, especially if you're learning a language. Now, it wouldn't be a talk from me without me complaining about a load of stuff. So I find it very hard to be you know, an evangelist about something, basically. So I'm going to tell you what I think is not good about Rust now. So Rust is really hard to learn. I've been programming all my life, and this language made me a beginner. So the ownership and lifetime thing is so strange when you first see it. It's very, very unfamiliar, and also, as we saw, the error messages are not very clear. So you really have to, it's like learning a new language of error messages to understand what the compiler is trying to tell you. It's also a large language, so there's a lot to learn. The language is also very young, and it's changing basically on a daily basis. So anything that you write today could not work tomorrow. That should change in the long term, of course. The language is just still young. The compile times can be very slow, although they are working on this. And some things are just really hard to do in what's called safe Rust. So everything I've showed you there is basically safe Rust. There is this keyword called unsafe, and this means I know better than you, let me do anything I want with my memory. It's basically like writing C in a different syntax at that point. So some things you absolutely do need to use the unsafe keyword for, otherwise you just can't get it through the ownership system. So some resources before we finish off. There's the website. It's all open source, so it's all on GitHub. You can try it online without installing it on they call it the Rust Playground. So it's just like you type the program into a web page and it shows the output. And this is probably the best place to start if you are interested in learning Rust. So that brings us to the end of the talk. I hope you found it interesting and it wasn't too, I don't know, geeky. Do you know what I forgot to do? I was meant to wear the hat. The Scrooge hat. Okay, so that's me done. Thank you very much.